A vector is an ordered set of values, all the same type. Vectors are useful in statistics because we typically want to deal with whole columns of data with many observations in them, rather than just one number at a time. You can use the function c to combine several values into a vector. The c function stands for combine. It creates a vector, an ordered set of data points, all the same type, and in this case, they're all numbers. So the c function here had 7 arguments supplied to it, each of them a number, separated by commas, all within the parentheses. And the result of that function was to stick those numbers together into a vector, which I've called age. Now age, even though it's a single variable, contains 7 values in this order. The variables that we want to analyze using statistics will almost always be stored as vectors in R. So it's important to know a little bit about how vectors work so that you can feel comfortable using them. Use square brackets to retrieve part of a vector. For example, I have this age vector that has 7 values in it, and if I follow up the age vector with square brackets and put in the square brackets the index 1, then I get the first age in the list, 34. If I use 2, I get the second age, 61. And I can use 1:4 to get the indices from 1 through 4, the first 4 ages in the vector. The reason this works is because 1:4 creates its own vector, and the elements of that vector get used as indices in the square brackets in the above line of code. So I could have used C again to combine 1, 2, 3, and 4 into a single vector to get the same result as 1:4. Either way, putting that vector inside of the square brackets tells R to give me elements 1, 2, 3, and 4 of the vector age. You can assign values to part of a vector too. So here's age again. It has these 7 values. Now I'm going to run this line of code, age square bracket 2, and then the assignment operator, and 90. I'm taking the value 90 and assigning it to something, but now that something is not just a name on its own. It's a name with a subsetting component, specifying the second element is to be worked with. And the result is that the second element of age has been changed to 90 from 61, and the rest of age left intact. The C function can also combine multiple vectors. So if I have 2 vectors, x is the numbers from 11 through 14, and y is the numbers from 21 through 23, then if I run the command c with x and y as its 2 arguments, I get a single vector with 7 elements, 11, 12, 13, 14, 21, 22, 23. Arithmetic functions are applied to vectors element by element. So age now is 34, 90, 20, and so on. And if I ask R to compute age plus 100, it gives me 134, 190, 120, and so on. Adding a constant to a vector is interpreted as adding that constant to each element of the vector. Similarly, age divided by 10 takes each element of age and divides it by 10. And square root of age takes the square root of each element of age. Log of age takes the log of each element of age. There are several commonly used functions that you should know about to find the properties of a numeric vector. Length is very important. Most of the time in statistics, we're working with vectors much longer than 7, so we don't want to just count how many elements there are. The length function will tell us how many elements there are. You can also calculate the sum of a numeric vector, the mean, the variance, the standard deviation, this is sample standard deviation and sample variance, the minimum, maximum, and median. Vectors don't have to be numbers. There are also character vectors. For example, here I have created a vector called fruit and populated it with a vector of 6 elements: apple, pear, fig, apple, apple, and pear. So now fruit is still a vector with 6 elements, but the elements are strings instead of numbers. The table function is useful for many kinds of vectors. Here it tells us that there are 3 apples, 1 fig, and 2 pears in this dataset. Elements of vectors must be the same type. If I try to create a vector by combining the numbers 1 and 2 and the string apple, it will convert those numbers to strings on their own. The whole vector got coerced to the string type. It started to rain, so I've moved inside. We'll talk more about data types later. The only point that I want to make here is that we can't attempt to add 1 to the vector fruit, because fruit is not a numeric vector, even though the first 2 elements of fruit look like numbers, and they were originally numbers before I tried to combine them together with a string. The result is a vector that is stored as character strings. Each element of the vector is interpreted as a character string. And so trying to add 1 to it just results in the error message that we're trying to do addition with something that's not a number. Now I want to show you the functions for correlation and linear regression. And for these, I'm going to work with some example data. So I'm going to create a vector called difficulty that just combines these numbers, and a vector called RT for reaction time that combines these numbers. So here, difficulty is on a scale from 0 to 100, and RT, the reaction time, is in milliseconds. This is not real data, and I don't even have an actual experiment in mind for it. It just represents possibly that making a task more difficult slows down people's reaction time. The core function allows you to calculate the standard Pearson correlation coefficient by default. So the correlation between difficulty and reaction time here is 0.78. This is just the correlation coefficient itself. If we want a formal hypothesis test of that correlation coefficient, then we can use core.test and we get a bunch more details. But don't worry about how this test works just yet. We'll talk about that in a future class. Here's how you might make a scatter plot of these 2 variables. I just ran plot with 2 arguments, difficulty and RT, and I got this plot. So difficulty is on the x-axis, RT is on the y-axis, and I can see the positive association that the correlation indicated. The LM function allows us to fit a linear regression model. This function works like any other function in R. You supply arguments in the parentheses, and the function returns a value that you can then look at or use in some more complicated calculation. But it's a little bit less intuitive for beginners sometimes. The first argument here is not just a single vector, it's a formula specifying the model that I want to test. And in this case, this is the only argument I've supplied. The tilde does not separate arguments. It's part of the formula. The tilde in a formula separates the response variable from the predictors. First comes the response, then the tilde, then any predictors in the model. We will talk a lot more about regression next class. But notice for now that this line of code produced output. That output is a representation of the value that the function returned, which is actually a list of a bunch of statistical details about this regression model. You can store this list in a new variable instead of just seeing the output at the console. Now I've stored it as this new variable called model, and model contains the complete output of this regression model. This is handy because often I want to do other things with the output of a linear regression model, including looking at a summary of that model using the summary function. So here, I get much more useful details about the regression model. It's very handy to know how to look up the documentation for functions. All functions in R packages and in base R come with documentation, usually available on the internet. And there are 2 main ways to access that documentation automatically from the R console. One is to run the command !, followed by the name of the function. So here I ran !binom.test to show you an example of looking up the documentation of a specific function, in this case a binomial test function. And what it did is open a page in my default web browser with that documentation. If you're in RStudio, it will attempt to open this same page but display it in the lower right quadrant of the RStudio interface rather than in your default web browser. Another way you can get the same documentation is by calling the help function with a single argument that's the name of the function you want help about. This does the same thing as the question mark. And it's useful to spend a moment walking through the pieces of those documentation pages because they can look a little bit intimidating at first. The first part of the function documentation is a simple description. So this one tests a null hypothesis about something like a coin toss, whether a probability obtained from a proportion calculated from the results of an experiment is significantly different from some fixed hypothesized value for that probability. The second part of the documentation page shows a brief summary of the arguments that the function can take, along with their default values if they have any. If there are multiple values listed here, like in the case of alternative, then the first one is the default. The third part of the documentation page lists each argument with details about how you use it. Then we have a section of the documentation page called Details that gives you an explanation of what the function is doing with considerably more detail than the initial description. And finally, a section called Value that explains what output the function gives. Usually, statistical functions will give an output in the form of a list, and that list will have many elements, and each element will be explained here. Most of the time, when I look at the documentation page of a function, I'm either looking under the usage heading to figure out what the default values of its arguments are, the arguments heading to get an explanation of a particular argument that I'm confused about how to use, or the value heading in order to understand what I can obtain from the output that I got from that function. You can use the question mark to get help about any kind of function, including functions from packages that you've loaded. For another example, you might try it with the lm function. That's a very handy documentation page.